Hi folks, and welcome back to Physics with Captain Rod. I'm making this video here to introduce you to the concept of the electric field and how it's mathematically defined. So in this example, I've got a pair of charges right here, both positively charged. One I've called Q1, another one Q2. And we know from basically observation here that there will be a force between these particles because they're charged. In this case, that force will be a repulsive force because they're both positively charged. So I can go ahead and maybe put force vectors in. Right? And that's the force called the Coulomb Force, the force that I talked about in a previous video. Now remember mathematically that the Coulomb Force is proportional to the two charges. So it's equal to K, Q1, Q2 over the distance between them squared. So in this example, this is going to be whatever that distance is. Now imagine that we put a curtain up or something, and we're observing this particle over here. So with the curtain in place, we don't see this charge over on the left. All we know is that we have to apply a force to this particle to the left to keep it from accelerating away. Or we know that whenever we let that particle go, it accelerates off to the right. So this is a force that we can observe quite easily. So because we cannot see this other charge, we have to ask ourselves, all right, what is it that's creating that force? And the what is it part, that is what is called, or given the name, the electric field. So we're going to say, all right, we're observing a force acting on this charged particle. That force is coming from something that we're going to call the electric field. The electric field is a vector quantity, so you have to define a magnitude and a direction. And here's the mathematical definition of the electric field. The electric field vector is defined as force per unit charge. So its units are going to be the Newton per Coulomb, and the direction of the electric field is given by basically the direction of this force. So that's how the electric field is defined. We can describe then the electric field around charged particles using a magnitude and a direction. Now, if I were to take this charge and maybe put it over here to this point in space right here, by observation, I would know that the force exerted on this charge would be kind of down and right, directly away from charge 1. So the electric field vector is going to equal this force divided by whatever the charge is here. Now you notice that pretty well no matter where I put a positive charge, whether I put it here, 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 the force direction is always going to be away from the charge, original charge. So we say that, all right, this charge Q1 is creating the electric field. And because of how the electric field is defined, the force direction will always be directly away from that charge. So as a general rule, forces are away, or electric fields point away from positive charges towards negative charges. Now we're going to talk a little bit about how electric fields are calculated, as far as how do we calculate an electric field. So I don't need this stuff. Let me get rid of some of this. All right, so we're going to go back to this animal right here. So the electric field we know is equal to F over Q. Now this Q in this example would be Q2. And the F, by Coulomb's law, we know can be written K, Q1, Q2 over distance squared. So if I replace the F with how it's calculated with Coulomb's law, then we're dividing by Q2, So this is force over Q2. This expression simplifies to K, Q1 over distance squared, This is the expression for how electric fields are calculated around a point charge. The electric field is proportional to the charge creating it, falls off with distance squared. So I'm going to go ahead, take a moment now, clean up my picture, and go through an electric field example. Okay folks, I'm back, cleaned up my picture a little bit. What we're going to talk about now is just a singly charged particle. So in this example, this particle is a point charge particle, meaning that, you know, all the charge is basically at one point in space from our viewpoint. And we're going to talk about the electric field around this particle. So now, you know, let's think about how electric fields are calculated. The electric field vector, the electric field vector is defined as force per unit charge. So, doggone it, looks like I got that a little bit too high on the page. All right, so the electric field vector is defined as force per unit charge. So what that means is this: if I pick a point in space, like right here, imagine putting a small positive charge there. If I say measured the force to be, I don't know, maybe 10 newtons, and the charge that I put at this point in space were something like 2 coulombs, then the magnitude of the electric field vector would be 5 newtons per coulomb. Right? Now, what I could do then is, you know, I could actually represent that with a vector, and that vector would point to the right. 5 newton per coulomb. Now, as far as, you know, how would I calculate that other than that example? Well, the electric field is equal to kq over r squared. So in this example, presumably this charge would be whatever it would need to be. This distance would be whatever it needs to be, so that when you calculated kq over r squared, you would get 5 newton per coulomb. Now you notice that that electric field vector points to the right. Right? That's a consequence of how the electric field vectors are defined. Long story short, electric field vectors always point away from positive charges, and that's because of it's a consequence of this, how the electric field vector is defined. Electric field vector is defined as force per unit charge. Here's basically how you get the electric field direction for any point in space. You pick a point, like right here. You ask yourself, if I put a positive charge there, which way would the force be? And the answer is, because it's plus plus, the force would repel it. So the electric field direction at that point would point like so. If I picked another point in space, maybe here, right, and then you imagine putting a positive charge there, because it would be a repulsive situation, the force would be kind of down and right, so the electric field vector would go that way. If I pick a point like right here, the electric field vector would point this way. Right here, the electric field would point this way, and so forth. Now, I'm drawing these field vectors all about the same length because, remember, the electric field, when you calculate the field due to a point charge, it's kq over r squared. In this example, this distance, this distance, this distance are all roughly the same. So because the distances are the same, then the electric fields would be about the same. Anywhere, basically a circle, maybe that looks roughly like this, you know, real roughly. Right? If I went further away, say out here, the electric field vector would point away from that charge, but the field would be quite a bit weaker, so I would represent that with a smaller vector. A point like right here, again, the field would point away, but again, weaker, away, weaker, away, weaker, away, and again, weaker. The further out I get from this charge, the weaker the electric field. So you would represent that with smaller and smaller electric field vectors. So now, basically what I'm mapping out is a field of vectors. It's actually called a vector field. And the vector field kind of describes the electric field around this charged particle. Presumably, if I knew the charge and the distance, I could calculate a number for the electric field vector at any point. And then the electric field direction always points away from the positive charge. I'm going to go ahead and pause this for a moment and take a look at a negative example, or an example of electric field vectors around negative charges. I'm back here, and here in this example, imagine we have a point charge here. I like to draw my negative charges in green. Imagine that this point charge is negatively charged, meaning that it's got extra electrons. Right? If I were to draw electric field vectors around this charge, here's how I would do it. I pick a point in space, like right here. I ask myself, if I put a positive charge there, what direction will the force be? Right? Taking note that plus, minus, the force direction would be to the left. Therefore, that is the electric field direction at that point. If I pick another point, maybe down here, and I ask myself, if I put a positive charge there, which direction will the force be? Right? The answer is up, because again, it's an attractive force, positive and negative. Therefore, that's the electric field direction. You'll notice that the electric field vectors all point towards this particle, and again, that's just a consequence of how the electric field vector is defined. You tell the field direction by assuming you're putting a positive charge there, and then the force direction tells you the field at that point. So as a general rule of thumb, electric field vectors point away from positive charges towards negative charges. Right? And again, presumably I could calculate the magnitude of any one of these electric field vectors by kq over r squared, if I knew a q and an r, k being the Coulomb constant, 9 times 10 to the 9th. So there's a little bit about how to calculate electric field vectors. I'm going to go ahead and make some videos that go through some numerical examples of both 1 and 2 dimensional problems. So hope this helps. Have a nice day.